So let's talk a little bit about why it is that bonds themselves actually form. So there are two models for describing covalent bonding. In this course, in this first semester, we're going to be sticking pretty closely to valence bond theory. Molecular orbital theory is also out there. That will play into a little bit more importance in our second semester in here, especially when we're talking more about double bonds and we're talking about systems of double bonds. So let's spend some time talking about valence bond theory. I'll give you just a little introduction to molecular orbital theory, but we won't worry too much about that at all. So valence bond theory, let's see what we say about that. It describes covalent bonding as the overlap between two single electron orbitals so that their electrons can be shared. So this is consistent with our little bonding pictures that we had before. The new thing here is that we have orbitals themselves that are actually overlapping. So I have two hydrogen atoms, right? Each has just a single electron in its 1s orbital. So hydrogen is just 1s1. Okay? I'd have drawn it like an H with a dot before. Those two 1s orbitals, when those hydrogen atoms get close enough together, there is some overlap between them. So that's the region where we say that the electrons are shared between them. Now, look at the directions of these electron spins. In order for those orbitals to overlap and for those two electrons to coexist within this space, they need to have opposite spins. So a hydrogen with a spin-up electron will be able to combine with a hydrogen with a spin-down electron in order to form this covalent bond between them. So what we get as a result of this is actually a new orbital that exists between those two atoms. So here's a picture of that new orbital. It's sort of cylindrical, kind of tapers off towards the sides, sort of like an egg, but it's cylindrically symmetrical. So this is a brand new orbital. Okay? Those two electrons that are shared now will occupy this entire space. Okay? So if we looked at it, down the line, okay, where I was looking down the HH bond, that bond would be circular. It would have circular symmetry going around it. Let's just say that way. So that's why it's more like a cylinder. So this is a bond. It goes directly between two nuclei. So the electrons are spending most of their time actually literally between the two hydrogen atoms. Okay? So there's one hydrogen nucleus, there's the other. The electrons spend a lot of their time right between the two nuclei. Okay? So when that's the case, that's called a sigma bond. So this is a Greek letter sigma, sort of make it like a number 6 that's turned on its side. Okay? That's a sigma, lowercase Greek letter. Sigma bond is just a covalent bond, a shared pair of electrons that exists directly in between two nuclei, in between two atoms. Right? So let's talk about what actually happens when those two hydrogen atoms come together. We alluded to this a little bit ago, that when bonds are formed, energy is released. Hydrogen atoms themselves are really very unstable. They're unhappy because they have only one electron. Their 1s orbital is only half full. Right? An element like helium with 2 electrons in there is fine on its own, but hydrogen only has 1, so it's going to need to do what it can in order to get those 2 electrons in the orbital there. So when the 2 hydrogen atoms combine to make that H2 molecule, turns out 436 kilojoules per mole of energy is released, because energy is given off. So here's a little diagram here. I have 2 hydrogen atoms. Okay? Those 2 are higher up in energy, okay, than the H2 molecule. So that 436 kilojoules is released when the bond forms. What do you suppose that means about having a hydrogen molecule and pulling those hydrogen atoms apart from each other? Well, these energetic processes are always reversible, right? But we have to do the opposite thing with energy. So if I just take two hydrogen atoms and I toss them together, it will release that 436 kilojoules of energy. If I have a hydrogen molecule already and I want to pull those two atoms apart, okay, it's going to take 436 kilojoules of energy in order to do that. So that energy has to be absorbed when the bond is broken. So think of those two atoms as like magnets. Okay? When you just toss them together, they'll fly together on their own, and you'll hear a bang, and they might even break if they flew far enough towards each other. So that's energy that's being released. Okay? If you have two magnets that are stuck together, it's going to take your own energy to pull them apart. You're going to go and struggle a bit if they're really stuck together. So it turns out that if this H2 molecule were two magnets, you would have to apply 436 kilojoules of your own energy in order to pull them apart, right? So always think about it in those terms, that two atoms, they want to fly together. It's because those electrons are attracted to the positive nuclei on each side. It's just that electrostatic attraction. So that's what actually causes bonds to form. So which is more stable? We talked about high energy and low energy. Is the hydrogen molecule more stable, or are the two hydrogen atoms more stable? Well, if something is stable, it's actually going to be relatively low in energy. If something is unstable, it has a lot of energy to it. Right? These two hydrogen atoms, they have a lot of energy, which means they have the capability of changing, of doing something. Okay? These two hydrogen atoms, they have the potential, that's why it's called potential energy, of forming that bond. So the hydrogen molecule is a lot more stable than those hydrogen atoms. Okay? And that's indicated in this diagram by the H2 molecule being lower in energy. So, and that 436 kilojoules, it's referred to as the bond strength, right? So the molecule would need to absorb that 436 kilojoules in order to break that bond. Okay? So we'll refer to bond strengths a bit throughout this course. Some bonds are obviously going to be much stronger than others. Some bonds are going to be weaker than others. So if I had a bond that was only 100, right, let's just imagine 100 kilojoules per mole. Is that a stronger bond or a weaker bond than the HH bond? Well, think about it. We needed to absorb 436 kilojoules in order to break the HH bond. I only need to absorb 100 kilojoules to break this other bond. 100 kilojoules per mole is a weaker bond. Okay? So a big number in a bond strength is a very strong bond. That's how much energy it's going to take in order to break that bond. So ultimately, it turns out that bond length is sort of decided by two opposing factors. If the two nuclei are too far apart, then those electrons aren't really attracted towards each other. There's really no benefit to it. And if I continue this at infinite internuclear distances, then we essentially have the two individual atoms, right? So that's what this relative zero is here, two individual H atoms. As we bring them closer together, we get energy released. Okay? There's that energy benefit in bringing negative and positive particles closer together. The negative electrons in those hydrogen atoms attracted to the positive nuclei. So there is an optimal bond length, turns out like 74 picometers in HH. But if I push them closer together, we end up with an unfavorable interaction. Why do you suppose that is? Well, you have an H nucleus in each atom. Both of those are positive, right? If those are too close to each other, those H nuclei will actually be repelling. So there's two things that are sort of optimized here. Okay? The bond length is close enough together so that the electrons are attracting with those nuclei, but not too close that the positive nuclei are pushing each other apart. Okay? So that's where this optimal bond length comes from. That's why each covalent bond has a pretty distinctive bond length to it. So HH bond is this different distance. Different atoms will have different distances. Most of them will be longer than the HH bond because hydrogen is such a small atom.